So thank you to all of you. Thank you here for those who are here physically attending and for those who are online. So welcome. This is the training workshop of START project. Okay. So we will bring here today, we'll have experts on the area from research, industry, and we will explore during the all day all topics related with the thermoelectrical value chain, from raw materials to devices applications, and also sustainable assessment. So we'll have not only speakers from the consortium of the START consortium, but also external speakers from outside the consortium. And I want to thank you to all of you for accepting your participation here, Professor Cornelius and Professor Antonio Gonçalves. Okay, thank you. So you have here, you don't have here the program, okay, the program was there. So we'll have the afternoon will be dedicated, I will present, giving you a presentation of the START project, okay, some insights and some results. And then we will give an overview of the thermoelectrical materials, sustainable thermoelectrical materials, which will be given by Professor Antonio. Professor Cornelius will speak about the applications of thermoelectrics, and then we'll have our colleague Luis about the special topic of raw materials obtained from mine wastes. Between that, we will have a coffee break. After that, after the presentation of Luis, we'll have the lunch time. And then we'll begin in the afternoon by talking about the processment of thermoelectric materials and characterization of thermoelectric materials. And then we'll go through the thermoelectrical devices, which will give by Hani from Thermorgy, from RGS. And also Eduardo will give his talk about the sustainability in thermoelectrics and the case of START project. So thank you all of you again. So let's start. I will give you start my presentation about the START project. Yeah, okay. So, as the title shows, I will present you the main result, the main objective and what we have implemented in the program of the START project. So, starting by the consortium overview, we are a consortium composed by 40 partners, including 6 research organizations, which I highlighted here in red, okay, which is Neves, ICME from Spain, Geosphere Austria from Austria, Skuj from Slovakia, and BGR from Germany. These all are geological surveys, and also we have SINTEF. The consortium is also composed by 6 SMEs. MBN Nanomaterial from Italy, related with the processment of the materials. Core with the sintering of the materials from Poland. Technology and RGS dedicated to the device production and development. 3 drivers dedicated to the sustainability assessment, and La Palma Research Center dedicated to the exploitation activities. And also 2 international associations, EPMEI and ASME, which were more involved in the dissemination and communication activities. With that, we covered with this composition of all partners, we were able to cover all the full supply chain that goes from the raw materials geology area to the material processment and development of devices, and the sustainability assessment. As you see there, the project started in 2022 and it will be completed by the end of May this year. So it already ran for 4 years. It passed very quickly. So what were and are the main core objectives of the START project? So we intended to convert mine waste into thermoelectric materials to develop tellurium-free thermoelectrical device. And in that, we intend to promote a sustainable European thermoelectrical supply chain. All these main objectives have a strong alignment to sustainability topics because we promote efficient raw materials use. We are promoting the recovering and valorization of mine waste materials, and all of that is very well aligned and supports some EU priorities, mainly those related with the European Green Deal, the Critical Raw Materials Act, the Circular Economy Action Plan, and also with some Sustainable Development Goals of the United Nations. A brief, very generic overview about thermoelectrics. So this will be given in much more detail in the presentations for next to mine. So this type of devices are able to convert directly it into electricity. This is a significant and important advantages of this type of technology, because if you think a significant share of the industrial energy, around 20 to 50%, it depends, is lost to the environment as waste heat. And that heat can be recovered by using this type of technology. It is a solid state technology with no moving parts, so there is zero direct emissions, and they can be scalable, and we can produce versatile devices also. Why this is important? Okay, because if you think in terms of sustainability issues, we are promoting with this technology energy efficiency, because by capturing that waste heat, for example, from the industry, engines, or the environment, we are supporting the decarbonization, enables maintenance-free power, which is ideal for long-term, low-maintenance applications, and they are able to be used in a wide range of applications, besides the ones that are already mentioned, in sensors, wearables, IoT devices, and so on. However, there are some limitations, okay? I divided here in two topics, technical and economic, and related with the raw materials. So, regarding the first topic, technical and economic limitations, we can talk about the low conversion efficiency of this type of devices, the high system costs, and the gap that still exists between what is done in research and what is really needed for the real applications. There is some gap between there. And that is why it is important projects like START to reduce or eliminate that gap. In terms of raw materials, we can say that, for example, you can easily buy thermoelectrical devices from small ones from the website, and those are mainly composed by tellurium-based materials. And tellurium is in fact a problematic element because it is a scarce element, expensive, and geopolitically sensitive. So, and these two aspects limits the European production capacity. So, what are some strategic implications of this type of limitations? So, it implies a supply chain vulnerabilities that impedes the the deployment of this technology. And to taking into account those limitations, Europe needs to promote material diversification and in order to reduce import reliance. And one approach that can be used and that we applied here in the START project is that mine waste can offer a circular and local alternative supply chain for this type of application. So we have chosen, as I mentioned before, we develop thermoelectric materials for mine waste with a focus on tetrahedrite materials. Why tetrahedrite? Because it is an abundant element, widely available, and by the fact that it is relatively abundant in some copper mine tailings, it promotes circular economy principles, and also it promotes the reduction of reliance on critical raw materials needed for the thermoelectrical technology, and enables a more sustainable thermoelectrical value chain within Europe. So in this European map, you see many different circles that corresponds to the different potential locations of tetrahedrite, and you see that it is a wide spread between the different countries, European countries. For the implementation of this activity, we intended to implement the program basically into 5 main stages, main phases. The first one was more dedicated to the sampling of raw materials, processing of the minerals, which is the first one there, recovery and reuse of mine waste. So we identified the potential localities to sample the tetrahedrites material. We processed them and incorporated into the processment stage for processing the thermal elements, which is the second stage related with materials processing. We used mainly powder technology techniques for processing the materials. Then there is a stage dedicated to the device development and production, scale up of some of the technologies that we applied for the material processing and validation process. Of course, in between, we needed to characterize very well all the materials that were used and processed by using advanced characterization. So what were the main inputs that we obtained from the implementation of the START program? So related with the first topic, value chain development, so we have identified European mine waste sites as raw material sources, mainly from tetrahedrite. Here, I hope you can see, perhaps on the back, it's difficult to identify the places where we identify as potential locations for sampling the tetrahedrite samples. So, but we identified a total of 17 locations from Portugal, Spain, Germany, Austria, Slovakia, and Austria. We only collected samples where we were able to access the sites, okay? For example, for the case of the Germany, so they identified 8 potential locations, but we were not able to access to those locations, okay? And we were able to process or to produce a total of around 40 kilograms of tetrahedrite concentrates. So by looking to the different locations, we see that in all countries that were within the consortium of START, we were able to identify several potential sites for sampling tetrahedrite. And this is really important because it supports EU strategic autonomy and circular economic goals. If you want to obtain more information about all this phase of the project, you can access to these documents, deliverables, D2.1, D2.2, and D2.3, which are access to the public. You can go to the Cordis page, for example, or to the Zenodo page of start. If you go to Cordis, you just put the reference number of the start project, and then you can access to the results and find those free documents, and you can have access to more details regarding the different sites that were identified, how the materials, how the quantity of the materials that was collected, and how the material was processed. But this is also will be presented by my colleague Luis in his presentation. But these documents are publicly available. So we were able to develop thermoelectrical, tellurium-free thermoelectrical materials using those mineral derived tetrahedrites. And for processing the materials, we were able, or we succeed in scale up the material production by using high energy ball milling, followed by spark plasma sintering. So we move from the lab scale to the pre-pilot scale and to the pilot scale. Here you can see it is in a small letter font size, but for the lab scale, for example, we were able to produce or process a maximum quantity of around 20 grams per batch. On the pre-pilot scale, around 300 grams, and on the pilot scale, around 1 kilogram. So the material were, after this process of high energy ball milling, was sintered by spark plasma sintering. And you can see here that in this phase of the process, we were able also to move or to go ahead from by processing 1 pellet to 12 pellets per cycle by using a different graphite dye, and we are were also able to sinter pellets with different shapes, from circular to square, as you can see here on this image. Regarding the performance of the materials that we were able to produce, so we achieved, I can say, significant results about the synthetic material. So we produce synthetic and a mixture also of synthetic and natural tetrahedrite. On the synthetic, we were able to achieve a ZT of 1.616. And for the mixture of mineral with the synthetic one, we are able to obtain the ZT of around 1. Regarding the device, so we defined since the beginning 2 main temperatures applications, one for the medium temperature applications and one for low temperature applications. So for the medium temperature application, for the medium temperature application, this is being done by RGS, now Thermoelectric in Netherlands. So you can see here a schematic overview of the device that is in production. And for the low temperature application, the idea is to produce a flex, what is called a flex tech by Technology in Denmark, with a size of, let's say, A4 paper page size. Sorry, this was supposed to, yeah. Regarding business innovation, we have also developed 2 business cases. So for each one of the applications, the first one is dedicated to a micro-combined heat and power thermoelectrical generator, and the second one, flexible thermoelectrical generator integrated with a solar device. This study is also available, publicly available in this deliverable, D.73, Business Models and Economic Studies. If you want to have a look to see some of the details and the results that are outlined there, you can also download the report and read it. We are also performing LCA and LCC analysis to compare the tetrahedrite base versus the conventional thermoelectrical materials. And more details will be given by Eduard later in the afternoon. Regarding social engagement, so we organize several workshops, webinars, and training events like this one, reaching to a higher audience in total, okay? We have developed multilingual cartoon stories, Starty, okay? We have now compiled all the volumes that were published in Total War 7. So we have compiled this in this book, in this version like this, okay? In English, this one, but it is translated into 14 or 15 languages. So we have here, we already have the translation in Japanese, for example, and also in Hungary. We also have developed a serious game which is called Energy from Waste Heat. We have a physical version, so you see here, you see here the board of the game. So the idea here is to promote the knowledge about circular economy and sustainable option and thermoelectrical topics also to all the public. The game is divided into 4 main stages, one dedicated to materials, the topic of raw materials, sustainable materials. Then there is a second stage dedicated to production, materials production, device production. A second one to use, applications of the devices. The third one to the post-use, what to do to in the end of the life of the device. This game is already available on a digital version. You can access it here. I think I cannot click here. I think so. But please try to access there, start game.eu. So this game, it is also, you have the possibility also to play in 10 to 12 languages. All the languages of the consortium partners are available here on this game. So, for example, it allows a maximum of 4 players. Each player, for example, can play on each language. So, and basically the game also is also the idea of the digital version. It's the same that the physical one. Okay, you need to move. You move from stage 1 to stage 2 to material stage, production, use, and post-use stage. Regarding legacy, all of that I talk about in some way, it's a legacy that we will be available to all of us. But we are also developing a start sustainable plan, okay? And we intend to, by the end of the project, to present Start Alliance to support the sustainable thermoelectrical ecosystem in Europe. This is still in development. And also promoted by the clustering activities of the START project with other European projects like TrWshop. We were able to go through or obtain the cost action, which is already running. It's called Sustanet, and it is dedicated to the sustainable thermoelectricals to create an European network related with that topic. It is divided in 4 working groups. You can see there, it is already running. And also, it has the advantages that it promotes the several networking activities. One of them are dedicated to give funds for scientific short-term missions and for conference grants. So they are already open. Okay, so if you are interested in having or applying for some of those grants, you need to go to the webpage of Sustanet and have a look to the rules and to the grants that are available. However, as everything, there are some key issues that still remain. One of them is related with the material issue and the use of mineral. So, as a natural or as a natural aspect of by using mineral materials, there is also an issue related with the variability and the presence of several impurities, which in some way can complicate and limit the processing of those materials. And that heterogeneity may affect the final thermoelectrical performance of those materials. Another issue is related with the regulatory challenges, the regulations that are in the European Union, mostly those related with accessing to mine waste sites or processing mine waste materials, for example. This is also an important aspect. Another one, which is not a limitation, but it's alert. We need current policies and also clear market signals in order to proceed with this technology. This is very important, okay? And also, we need a strong collaboration and coordinated actions between what is made in research, the needs of the industry and of the market, regulators and policymakers. This is very important also. And this is two notes that I just wanted to leave with you. So I'm almost concluding my presentation. I just want to highlight some key aspects of the START project. So we have promoted innovative raw material use. We converted secondary sulfide minerals that were collected in some European mine waste sites into high-performance toluene-free thermoelectric materials. This can in some way unlock new sustainable raw material resources for energy solutions. This in some way it's correlated with the critical raw material substitution and promote circularity also, which is fully aligned with the Critical Raw Materials Act. We also need to adapt the processing to the material that we are using. This required flexible and adaptive processing approaches, and the results that we obtained and the techniques that we have used really were very important, and it is a promotion. It will promote the EU competitiveness in producing sustainable materials and also for energy technologies, for the green transition, and also very important, the involvement since the beginning of SMEs. It's really important to promote innovation and the practical implementation of the materials that and devices and technology that we want to implement. And that supports economic innovation and the advancement of sustainable thermoelectrical technology in Europe. And before concluding, I want to acknowledge and thank all the members of the consortium START for the great work that they are developing and developed so far. So thank you to all of them, and thank you to all of you here.
Thank you very much, Philip. Are there questions among the audience?